recorded. I'm trying to understand what you're doing. It's good whiteboarding. Maybe you are talking about a differential equation, right? Maybe this is it's just I guess it's called a differential equation. For example, if I have a dy dx, right, equal to say equal to 2y, for example. So this is the question. What you can do, you can integrate on both sides. Do you agree? But before that, you can, in this case, you can also do some arrangement before you do it, right? You can do that. So that is integration on both sides. So yes, you can, like any mathematical operator, you can, or operation, you can use this treatment for an equation on both sides at the same time. I forgot that. Then in this case, you have to, so this is just a hypothetical issue, right? But to solve this particular question, I prefer to separate the variable first. Can you see? The step one, in this particular case, we have to separate the x and y. Separate x and y. And what we can do, we can divide it by y. Can we divide it by y? And then multiply dx. So that is a 2 dx. Can you see that? Can you see that's algebraical change, right?
Yeah.
Then it's easier to do integration on both sides. To do integration in this case, we just added this sign. That's all. Can you see? So this just like, so this operation is similar to, you have, for example, if you have the in algebra, so this is similar to the algebraical. For example, if you have y equal to x squared, right? So what you can do, you can, for example, in this case, we can, this is hypothetical question, so we can use a square root on both sides. Can you see? Can you see that the similarity? It's called analog. So then you will think. Then after that, you will think in physics, in integration. So what can we do about this two integration? So one is dy dt. Have you seen this kind of integral? Can you see? Can you work out this solution on the right hand side? Have you seen any function which can be integrated?
Oh, yeah.
Yeah, you do. You put the dy outside. Whoa, that is not allowed. No. You're not allowed. Oh, what did you do? You multiply dy. Did you put the dy outside or what?
Yeah, by multiplying. So
you can't. You cannot. You cannot. Now here we have to remember what we have learned in integration in the first place. We often write the function as we often write the function as such as let's just give an example. Y as function is a function of x, right? So if I have y equal to 2x, right? So we can also integration, but in this case, you have to add the dx, right? This probably is not a good example. Here, I just remind you, this is not allowed because the only expression we have seen, not this one, is this example. Can you see? Have you seen this integration? Dx over x. Have you seen this integration before?
no.
No? Are you sure?
Not with, I don't think, a value on top of it.
Well, you can, so this is, you can think that way. Okay. Do you remember the basic calculus integration, calculus principle is such, if you have a function, right? If you have a function x, you want to integrate that. After that, you will get something else, but still in general is a function plus a constant. Do you agree?
Mm-hmm.
So that is the integration all about. A function fx, the no case fx, after integration will become another function plus a constant, right?
Yeah.
But according to the basic theorem in calculus, the df, the first derivative of f, the capital F, dx should equal to the fx. You see?
Mm-hmm.
Do you have your teacher show you this pair of formula before? This is the essence of the integration. So after integration, you will get some different function. However, this function is related to the function f, lowercase f, by this simple relation. Have you, how far have you studied? For example, can we go to example, right? Do you know this integration, dx, dx? Do you know that after that, what is that?
X squared over x, I mean over 2.
X squared over 2, right? Did you say over 2?
Mm-hmm. Yeah,
yes,
plus
that's right.
C.
Plus C, yeah, that's right. Do you want to try? So this time, so in our case, fx, can you say here? In this case, in this simple case, that capital Fx is equal to x squared divided by 2. Now, can you show me? Can you prove that there's a simple relation? Can you find the first derivative of this function? So, what is the first derivative of this capital Fx?
Not
yeah.
df.
If you don't have use a prime, if you use a df dx, you just do it. Can you see? Because this is function. Can you see this is function?
Yeah.
What would you do if you ask it to do the first derivative? Can we just copy that? We can copy that x squared divided by 2. Can you see? So do you know this? Do you know this method? Do you know how to find the first derivative of x squared over 2?
Isn't it?
Yes, if you know this formula, how did you memorize? Did you memorize this, or do you know how to derive this formula?
I think
you memorize it, right? Did the teacher show you how to do that?
No.
Aha. So this is very, you got a log, right? Is this log, natural log?
Yeah.
Hardly. Let's just try again. If you just do something simple, okay? What is the first derivative of x squared? Can we just without that 2? What is the first derivative of that? Or in other words, what is the derivative of x squared? This is different. This is alternative but equivalent notation. Can you work out this? Yeah, this is a basic idea in calculus. In this part, this is how to find the first derivative given a function. Can we do some simpler? What is the derivative of dx? That probably will give you. So can we go to another one? How about dx? Or what is the derivative of x?
Oh, it's d.
Sorry?
D.
Are you sure?
I think
if we need to discuss this issue. So you can see dx are the same. Even
oh, is it just one?
Yeah, just one. If you just algebra, it's just one, right? Without use the formula, you know it's one. But if you do know this formula, that is a basic formula for calculus, that x to the power n, do you know this formula? Which can be written as dx to the power of n and dx. How do we know this? N is any number. It could be integer, could be a fraction.
Mm-hmm.
Have you studied this formula?
No.
Ah, maybe you are still not. Have you studied the first derivative formula? Have you studied this formula? It's very strange. You know the integration formula, but you still have trouble to know this one. Have you seen this formula in take one?
Yeah.
Oh yes. Why don't you use it? You see? Yes.
Yeah, we've just never.
You never use that. Yeah, you need to not practice. Because it's very interesting, because you obviously this is correct. So obviously you know this formula, which is correct, right? Did you memorize or did you find it from textbook? This is correct. This is correct.
We got a list of formulas of like
Yes,
derivations.
that's right. Yeah, in that case, that's why these questions remain a little bit challenging for you, right? Because when the reason I ask you this question, can you see my original question is here, right? I'm trying to remind you, no matter if you know this solution, just take opportunity. By the way, can we just discuss this issue? Have you seen this integration when the fx is 1 over x dx? This is the same, can you see? So I just rewrite this integration. This is the same. I just change, just make sure these are small fx, right? So in this case, fx is equal to 1 over x. Can you tell me which function whose first derivative is equal to 1 over x? What is f? What is f? Can you work it out? You can check your formula list. Yes, a natural log. That's right. That's right. So if you know this formula, so that's right. So this is exactly correct. Therefore, we should be able to solve this integral. Do you agree? Can we try again?
I thought it would be dy.
Yes.
lny.
No. Why did you have? You see, let's just do it again. Yeah, you see, this is similar. Can you see? When we do this integration, did we put dx outside? We didn't. So you cannot do this. You see, you cannot. Did you do this? No, you cannot say. You cannot put dx outside. You see, this is a serious mistake, right? You can only use the basic formula following this rule. So this calculus, this called sometimes called the theorem, basic fundamental theorem of calculus. Can I look at your textbook? Do you have digital textbook? I show you where is this relation. You should be taught now, because you already studying. You already are studying the integration now. I give you a green light. You can share your side. Did you have digital math textbook?
I don't have access to it anymore.
You don't have access to it, yeah. Okay. Well, what shall we start? Yes, it's very interesting, because I thought you have in that case, I just return to my whiteboard instead. Now you just go to basic, right? Today we need to go to basic. We know that this is one formula, okay? Another formula you just mentioned is that is a natural log x, whose first derivative is equal to, can you see? It's just a different notation of first derivative, right? That is x, that is equal to 1 over x, can you see?
Yeah.
How about EX, first derivative? That is the basic formula.
Mm-hmm.
Do you have this formula in your?
Yeah.
Oh, I don't think they have X. Are you sure they have X?
Oh wait, no, not X. It's just 1.
That's right. Yeah, you have to be careful. So don't confuse with this formula, right?
Mm-hmm.
So this is called the power function. So this is called the power function. It's called the power. They have a proper name. While this is called the exponential function. It's different. It's called exponential, right?
Mm-hmm.
Called exponential function. It's different function. As therefore, the differential function would be different. And in addition, how about sine first derivative? We can use x continuously. Do you know the first derivative of sine?
Mm-hmm.
Or d sine? These are the basic first derivative formula. Oh, I use theta again. I use x this time. Do you know the answer?
Yeah.
Yeah, positive, yes. Similarly, what is the cosine x first derivative? Yeah, that's right. Negative what?
Negative sine x.
Yes, that's right. You're right. How about tan? Do you know the tan? Do you know the chain rule and quotient rule?
Yeah. Tan
Yes.
is 1 over cos
Yes,
squared
yes,
x.
I remember. Yes, I remember one time you used this very this formula. It is yes, I guess you sporadically asked me a question which is inverse function. Do you remember last time? You are doing the inverse derivative. Do you remember? We are trying to work out the tan inverse function. Do you remember?
Yeah.
So last time. So obviously you have studied calculus for a while, right?
Mm-hmm.
So this is not the basic formula, but what that can be done by treating this as a product quotient, right?
Mm-hmm.
So according to quotient rule, do you know the quotient rule? That's v squared r. There u is equal to sine x. V is equal to cosine x. Do you know the quotient rule? That u v dash takes v u dash. What is order? You can check the order. Do you know this quotient rule?
Yes.
Can you double check if this is correct or not? Is other way around? Which is positive? Which?
No, that's right.
That's right. Okay, if that is
wait,
right.
no, it's not. It's
Other way around. Okay, so they should be. Yeah, let's just do it again. So we just use u dash first. We use u dash first. So we started from the it's a v u dash, right? Take u v dash. And normally I don't use this formula because we can also use the product rule as well. Did you notice that?
Yeah.
Anyway, that is how to use. So basically, these are the derived formula. Can you see? So this formula is called derived formula, and above that is called the basic formula, right? They call the basic formula or the derivative. And this is called derived because if you encounter the combination of the simple function, then you can either use a product rule or chain rule or chain rule. Do you know that another rule is a chain rule? Do you have 3 rule? Do you know the 3 rule? The chain rule, the product rule, and the quotient rule. Quotient.
Yeah.
Quotient rule, right? They have 3 rules, so you can use either of them. Now return to this question. I guess what we are studying is how to solve the differential equation, right? Because I just pick up the wording from you that you integrate. Did you ask me integration on both sides? Yeah. So that is a method how to solve an differential equation. Differential equation, okay? Not algebraic equation. Equation, what is a differential equation? Any equation that involves the first derivative or second derivative. Any equation involves the derivative is called a differential equation, right? That is a equation. So for example, let's go to first example. For example, the question is very useful. If you have the dy, can we just return to the first example, equal to 2y. So this is one integration. The reason it is an differential equation because in this equation you can see the derivative, right? A slightly challenging question is about even they sometimes have involved the second derivative. Can you see?
Yeah.
So this is another equation which involves the second derivative. Can you see that is that equal to? Can we say this is can we just derivative? Can just we just put any number here, right? So yeah, you can see, of course, you can get it more complicated. You should be able, you could expect that the equation could be getting more complicated like this. They contain this is general equation, this is general form. But in high school, we are not supposed to solve all of this problem. I write this down just for display purpose, right? You probably will see this one, the first, second derivative. And they have constant, right? Kind of sense constant here. Is a constant, they just use a constant, can use A. And then you plus constant B and the second first derivative, right? And then got a C, got Y, you see, and equal to something else. This could be another function, you see. But we just go to simpler one, you see. So this is similar to our algebraic equation, quadratic equation. Can you see that?
Yeah.
Plus C equal to 0. Can you see? So this part is called a differential equation, and this part is called an algebraic equation. Okay, algebraic equation. So to solve the algebraic equation, you don't have to use calculus, but to solve the differential equation, you have to use the calculus. In order to get the objective is that what is y, you see? Here we are looking for what is x, do you remember? Now, when we solve the differential equation, we are looking for an unknown function, not a constant. So what can we do? Did I remember? Do you remember the first step? I suggest to separate x and y. To separate x and y. Because in this case, we can use integration easily. If otherwise, it's difficult. Yeah, that's right. That's right. Perhaps we just keep the 2 here. It's easier because that function on the left-hand side looks simpler, right? And then step 2. So step 2 is just use integration. Can you see? Yeah. Just use integration on both sides. Then we should be able to use our knowledge of integration to solve this y function. See, so this side is dy y equal to. Can we put a constant outside? You can. You can only put a constant outside. You cannot put a dx outside, right?
Okay.
Okay. What can we do next? So to solve this equation, you need 2 pieces of knowledge, right? So what is the left-hand side? So the left-hand side is a dy y. Okay, can you solve this question now? We have discussed this. Do you have any proper formula? No? What is the fx? Because this function should give me something, you know, it's different function, right?
Yeah. Can I do it like this?
No, you can't. No, because there's no reason. Because if you want to use integration, similarly, you can do this. You cannot. So if you have y, you could. Can we just use this example, right? We can use a square root here on both sides, right? Okay, and then all of a sudden, you added another. So if you got this, you got the x, and you got to put it another way, I think you cannot do that. That's all, right? You see, I don't know if you are studying calculus, you have to stick with this form. I read the formula here. It's probably that will help you. If we don't use y, if we use x, you know the result. Do you agree? Which is the natural log, right?
Yeah. But what happens to the d?
Well, d means what? Tell me, what's your understanding of d? What does d means?
Derivative?
No, d for differentiation. She's very small to interval. Change. D represents the difference between the two adjacent points, which can be very small. Now, this is something probably you're missing so far, is that no matter which letter we use, can we change now? If I use F, we should also apply this formula in its form, not the letters. Can you follow me?
Yeah.
No matter what letter we used, we should be able to work out this form. Yes, that's right. So we solve the left-hand side. We need to find the right-hand side. So how do we solve the right-hand side? dx. What is it? Yeah, go on.
Is it equal to?
What is the function of this? Can we just put it here? That would be the function. Do you agree? Can we just call it fx? Can we just call x plus c, right? Okay, this is not a c. This is c1. Can you see c2? Can you see?
Yeah.
So what is capital Fx?
Is it x squared?
No. According to the, you see, this is probably we were spending some time to work out this what we call the principle or fundamental law of calculus. Can you see the relation again? The result after integration, capital Fx, whose first derivative must equal to the lowercase fx. So you really have to appreciate this simple relation. In other words, let's go to there. In other words, in this case, can you see? We don't, if you don't know fx, but we know that df dx must equal to 1 because this 1 is invisible. Can you see? So then you tell me which capital F whose derivative is equal to 1. Yes. Yes, you're right. You're right. Okay. And another thing, perhaps your teacher didn't mention that when you see this D and adjacent, close, very how to say, just behind the, if you can see this two notation is joining together. Can you see? There's nothing, but it's just two. Then you can just use, you can simply cross them, you see, and then got your result, which is a 2x. Yeah. Of course, apart from constant.
But you can't do that here.
No. They show me this. They probably your teacher didn't tell you this basic idea. I just show it again, right? If you see something like this, all right, which means that you can simply cancel it. Did the teacher tell you?
No.
Yes, I show you now. That's just x, okay, plus apart from the constant, right? Mm-hmm. And this is similar to our, for example, if you have the square root x, right?
Yeah.
And then you square them. Can you see this two? This is inverse operation. So what do you have?
X.
Yes, this canceled. Can you see?
Mm-hmm.
So you have to appreciate what does mean the d and integration. Okay, so this is x. Can you see? Mm-hmm. So this is similar. So in this case, this symbol means integration. Integration. And this symbol d means differentiation. That's why they use d, differentiation. Okay. So if you have a function, you're asked to do differentiation, but then you have to do integration, and these will cancel. These two operations will be canceled. Mm-hmm. And probably, if you haven't studied that, I will at this stage, I only show you this simple relation. All right. Mm-hmm. Now, so this is one way to solve this puzzle. Alternatively, I just extended this idea. So this is this example 1. How about example 2? If you have the d ex, can you write the result without actually doing integration? Oh, sorry, this is ex, not 2, sorry. Ex, yeah. Yes, that's right. Can you see that? If you see this good opportunity, you just cancel them.
Yeah.
Right? But you cannot do the one we just encountered. Can you see? I go to another example. So example, can we go to the example? How about the dx over x? Can you cancel them?
No.
No, because x is variable. You cannot cancel them, right?
Mm-hmm.
So in this case, you have to use a different idea by recording that formula. Can you see? Mm-hmm. Why? Because the first derivative of this formula, a natural log function, is exactly equal to 1 over x. Can you see? So this equation, so if I denote this as capital Fx, if I use this one, so if that is this is a small fx, all right? Mm-hmm. They also satisfy this condition. Can you see? In other words, d capital X dx is equal to this small x, which is a fundamental law, which is a fundamental theorem of calculus, right?
Yeah.
And also, although in these two cases, we can also use another formula. Can you see? So this is method 1. This is easy one. Okay. So this is method 1. Also, we can consider that method 2. On the other hand, we can also solve this problem. Can you see? By just write this result as ex, right?
Yeah.
Yeah. Oh no, in this case, we don't have method 1. We only use method 1, no method 2, sorry. Now, this just after this preparation, can we just attempt to solve this differential equation now? Can you see? Where are we? So can we just copy this, copy your previous, so given, return to that question, given dy dx equal to 2x, right? we have step one, we separate them. We just got dy. This is not, this is y, sorry. 2y. So we got the first step, we separate x and y. Then we got 2dx, right? Second, we integrate on both sides, do the integration on both sides, you see? 2dx, can you see? And the left-hand side one, we know that the dy dx, over y is equal to natural log y, right? Plus a constant. The right-hand side, if we just put the 2 outside first, dx, then we can use this method to cancel the integration and the differentiation. So in this way, we can directly got this is a 2x. You see?
Yeah.
We can get the 2x plus another constant, right? So if we combine these two together, so step 3, if I convert this formula, so what we have, we got a natural y equal to 2x plus a constant. Okay, so this c is I use just one constant now, right? So you can argue this c is equal to c1 minus c2, right?
Yeah.
If you want to know what is c, it's constant, so we don't. That is how we can you see from here to here we have almost solved the equation. Can you see? Before that, at the beginning, we are given a differential equation which contain a first derivative. After that, we found the equation without differentiation, right? However, the objective is to find the function. What is y? Can you use some basic logarithmic knowledge to solve this issue? Can we solve the y? Yes, that's right. Yeah. So in this way, we solve the y. Do you agree?
Yeah.
So we can find the function now. So that is the objective of solving a differential equation. Now to make it more compact, I can simply put another constant. Can we call it the a? Can we call the function a, the constant a here, and e2x? Do you understand? And a here, you can argue e is just e to the power c. Can you see? So you still got unknown constant. Can you see?
Yeah.
So this is a constant to be determined. Is another constant, right? So therefore, to solve the differential equation, you have to give in another condition. Otherwise, there will always be an unknown constant, undefined constant. But after all, we have found the form of the solution, right? I think that is what you are studying, I think.
Yes, I think so.
Yes. So if this is one issue, and I just want to remind you, not all differential equations can be solved easily, right? There are only a few cases, special cases, we can use this rearrangement to solve this question. We can try another example, maybe. So can we just try another example? How about a function? How about differential equation? Given a differential equation. Oh, sorry. Given a differential equation. Differential equation. This time slightly different. Now, this time is dy dx we put some constant here. Can you see? I put the x, we multiply x and equal to, and equal to y squared. Can you see? A little bit complicated now, right?
Yeah.
Can you find, so given that, can we find what the function is based on this differential equation? What is the function of y? Do you want to try? Remember the method we studied? We first have to separate x and y, right? Separate x and y. Otherwise, if you mix them up, you can hardly do differentiation, integration rather. Yeah, you divide it by x, that's right. What else can we do? Yeah, you multiply dx, that's good. You divide it arc square, good. You see? Done. Okay, that first step is done. The second step is just to do integration. Can you see? You just do integration. I use your color. So I use integration on both sides. That is an extended mathematical operation. When we solve the algebraic equation, we can always multiply, divide, or square root on both sides, or even use log, right? Similarly, we can also use the same mathematical operation on the both sides of equation, provided up. This x should be up, right? You multiply x, be careful. Yeah. This x should be here.
Oh, yes.
Yeah, this is not right. Okay. So in this way, we can integration on both sides. So in this way, we can use your color. So we got that is the question became how to solve these two integral, right? So what we can do? Just continue here. We can continue here. So how about the left-hand side? The left-hand side equal to dy over d squared. How can we solve this puzzle? Natural log? Oh, how? If that is so, can you test? Can you try? Can you prove this correct? I'm interested to know this result. See? No, doesn't matter.
Oh,
if you think it's right, just keep it right. But we have used. I show you how to use a criterion to check. All right. Okay. So this is all right. Even you get a wrong answer, doesn't matter. To check, how do we check? How do we check that? In this case, here. In this case. What is capital Fx? Can you tell me? What is capital Fx? Do you know that general notation? Integration lowercase x dx equal to capital Fx plus c. Yeah. So what is capital X? What is capital F in our case?
Is it 1 over y?
No. In your case, it's a natural log.
Oh, yes.
Y divided by 2y. Okay, to check, can we use this relation? I write down this here. This is something your teacher didn't tell you. It's very important. It's called the fundamental principle or fundamental theorem of calculus. So this must be obeyed. So the capital X must be satisfied this condition, whose first derivative must equal to this no Fx. All right. I just highlight this. I highlight this formula here. This is called the fundamental. Just check your textbook. This is called the fundamental or basic fundamental theorem of calculus. Okay. So this is very important formula. It's not the principle, it's just a simple relation. Okay, can we find the first derivative by using your knowledge to check, okay? At this stage, we just to check to see if this is correct. Use the chain rule, good. Okay. Good. Okay. If that's the case, does that, but this doesn't equal to 1 over y squared, unfortunately.
Yeah.
Therefore, fx in this case should not equal to your result. Can you see? So this is wrong. So this is wrong. But alternatively, can we find another way to solve this puzzle? You see, basically we are trying to solve this integral, isn't it? You see? If you, as I say, when you study algebra, you have to be flexible, right? Yeah. Even we haven't seen this y as a variable in the integral, but we do have seen that. How about this one? How about dx x squared? Have you seen this form? Have you studied this form? Do you know how to solve this one? No? Yes or no?
No.
No, but if I just rewrite it as a -2, do you know how to solve that?
Oh, yes. Oh, so do I do the same thing here?
Yeah, that's right. Can we find this formula first? This is useful. We can apply this formula once we know the solution, once we work out the solution. -1, are you sure? Yeah, I noticed that we have to do some more practice of the first derivative before we solve this differential equation problem. This is not true. So if I just use this formula, can we just show you what I do, right? Can we just show this as x power n? All right. According to our formula, so the result should be equal to n plus 1 and to the x n plus 1. Do you agree?
Yeah.
Oh, you are right. You are right. You are right. So -2, right? Did you use -2?
Yeah. So.
Oh yeah, yes, right. Yeah, you're right. Yeah, you're right. Did you use this formula, by the way?
Yes.
Oh, good.
Yeah.
Okay. Okay, you're right. Okay, you're right. Okay, knowing this is correct formula, and can we work out this? Can we work out the integral directly? So what is the left-hand side? Can you tell me by comparison? No. Oh, yes, right.
Yeah.
You're sweet. You're sweet. Oh, that's right. You're quick. Okay, that's fine. Can we put a negative sign here? This in front of notation. Yeah. Can we just rewrite it as -1 over y? Okay, so we solve this left-hand side. All right. How about the right-hand side? How about this integral? How about the right hand? So the right, can we have some space
that's
here?
Just ln of x.
Yeah, that's right. So therefore, finally, we got this equation. Can write down here. So we solve that one. We have -1 over y equal to. Do we have constant here? No constant. So that is just natural log x plus a constant. All right. So now I have combined the two constants together as one unknown constant, right?
Yeah. Okay.
Can we find y now? So this is what step now. We have the step 2 and 3. Yeah. Can we find what is y? Can we solve the y? Yes. Okay.
not negative.
We need to solve. We need to solve for x, for y. We need to solve. That's what solve for, or find the formula for y. Yes.
Y equals.
Yeah. Can we put a y on the other side?
Mm-hmm.
That is the final result. Can you see?
Mm-hmm.
Okay. Doesn't matter. You can put a constant. Yeah. You can here, or you can alternatively you can put a constant over here.
Oh yeah.
You agree?
Mm-hmm.
Because according to the product rule, we can rearrange that. All right.
Mm-hmm.
Yes, that is a solution of this problem. Perhaps I will suggest to do some exercise of the I just observed that sometime you let's just do some exercise. How about for the integration of the square root x dx? Do you know how to solve this integration?
Yes.
Yeah, you can use that general formula, right?
Mm-hmm. Does this equal? No.
Yes. Not negative, not half, not negative. Without negative, this is square root x is just equal to x to the power half. Yeah, positive. Yeah, yes, okay. Yeah, apart from constant. Yes, that's right.
Mm-hmm.
That's right. Yeah. So I show you. Obviously, you are using that formula, right? Here you are using the formula. I know you are using the formula, but now I teach you how to use without use formula. We still can solve this problem, right? For example, can we just write this formula here? So that is x n plus 1 divided by n plus 1. All right. From the constant. Now, without use formula, can you see this time I show the different method? All right. This method is used that fundamental theorem of calculus. For example, if we have the x to the power of 1.5, right? For example, okay. But I know that the result would be just the constant x to the power 1 plus 5 plus 1. Can you see? I pretend we don't know the formula, but we know that this index must be correct. Can you see in the first place, plus another constant d, all right? So this time I will invoke, or we're going to use this fundamental theorem we just learned this time. Do you agree? This is small fx, all right? So what do we do? I just do the first derivative of df. Can you see? So from here we can work out the first derivative is equal to, can you see? That is a c divided by, can you see? 1.5 plus 1. We can put this number together, okay? Put the two numbers. That's a 2.5. Can you see? And that is to the power of x 1.5. Can you see?
1.5 or 2.5? Sorry? Is this 1.5 or 2.5? For cx?
Wait a moment. I'm trying to follow this. I'm trying to follow this one. It's a sum, because can we just say, can we rewrite this as x to the power of the 2.5 at the beginning?
Yeah.
We are doing the first derivative. Yeah, that's right. So we put a c divided by 2.5, and that is x to power 1.5. Can you follow me?
Yeah.
Okay. We know that in this case, small fx is equal to x to the power 1.5. Do you agree? Now, according to this fundamental theorem here, the first derivative of capital Fx must equal to the lowercase fx, right?
Yeah.
So therefore, so based on this, so because df capital X dx must equal to the no case fx, right? Therefore, we can set up equation. Can you see? That equation is c divided 2.5 and to the power x to power 1.5 must equal to the small fx, which is f 1.5. Can you see? Can you follow me?
Yeah.
So therefore, what is c? What is this unknown constant c here?
2.5.
2.5, yes. So we solve this problem, do you agree? So therefore, we this time I just pretend I don't know this formula, right? But instead I use this so-called the fundamental theorem of calculus, right?
Yeah.
Because it's boring. It's simple. You just use the formula, right? After a while, you have to know the reason why there is a formula there. Because the fundamental theorem of calculus will tell you after integration, the result whose first derivative must equal to the function integrated.
Yeah.
I think that is what we can discuss. Yes, you have balance. You see, last time you are starting the challenge question, I remember. Do you agree? Last time this is called how to work out the inverse function. You remember? So do you still remember that form method? Yeah. And I consider this is a more challenging, this is a high level calculus question. But you have built the a good foundation to learn to start calculus. All right. So as you can see, we can, in principle, to solve a differential equation, provided we know how to do integration, right? Because to solve the differential equation is to get rid of this integration, first derivative. Can you see that? The solution should not involve the derivative. That is how to solve the differential equation, not algebraic.
Yeah.
Okay, probably I will save these pages. Can we stop here today now?
Yeah.
Okay.
I will see you next week.
Next week. Okay. Okay. Take care. Goodbye.
You too. Thank you.